In today's video, we'll be showing how to set up the BNI00L7 or BNI00L8 within the Codesys programming environment. Both modules would be set up exactly the same, independent of which one you choose. A couple quick review notes on the BNI00L7 and BNI00L8 from BALF. They are 16-point configurable I/O modules. They utilize the M12L coded power. They are multi-protocol with EtherNet IP, Profinet, EtherCAT, and Modbus TCP. In this video, we'll be concentrating on EtherNet IP. They have built-in REST API and MQTT for IoT control. With the L-coded power, we can provide 16 amps of current on both the input and output side of the power, with 2 amps being available per output on this module. The black line, the BNI00L7, has a composite shell that is weld splatter resistant and has no display. The silver line, the BNI00L8, has a die-cast zinc nickel-plated shell, and it has a display where you can set the IP address, subnet mask, gateway address, and protocol through that display. I will be using the BNI00L8 in this video. Also for this video, I wanted to point out that the L7 and L8 are both sitting at hardware 1.0.3 at the time of filming, as well as having a firmware of 1.4.0. The Codesys environment that I will be using a Raspberry Pi for my controller, the revision level is 3.5 with Service Pack 22 with Patch 2. So let's move into the Codesys environment and show how this is set up. So I have my Codesys project here in front of me. I'm already pointed at my controller. So the first thing we'll need to do is go to Tools and go to Device Repository, and this is where we'll need to load in the EDS files. The EDS files can be obtained from the BALF website. I'm going to click on Install. And I've got already the folder with the BNI00L8 EDS file in it. So I'll open up that folder and I'll point to the EDS file and click open. And we get the message that that particular EDS file was loaded. So we can close this out. In the left window here, I'm going to right click on the device. I'm going to add a device, and I'm going to open up Ethernet IP adapter and click Ethernet. I'll click Add Device. I'll click on the Ethernet, come back to this window, and I would choose Ethernet IP, Ethernet IP scanner, and then choose the Ethernet IP scanner device, and I'll add that. Moving back to the left window, I'll click on the Ethernet IP scanner, and now I have all of the BALF loaded EDS files as well as the generic device provided by Codesys. I'll click on this BNI XG3 302 1B5 Z067, and luckily down here it tells me the short order code is the BNI00L8, which is the device I want to add. I'll click Add Device, and I'll click Close. Now to continue on the setup, I'll need to go to Ethernet and double-click that. I'll click Browse and point to my Codesys controller. Click OK. And then I'll come here to the BALF module, double-click on that. I'll need to set the IP address, which currently is sitting at 192.168.11.107. I'm going to come here to Connections, and in this lower window here, let me close this one. In this lower window, you'll see that there is a Pin 4 mode and a Pin 2 mode for each individual pin on this module. Here's what this is involved. Pin 4, there's no choice. So pin 4 is always going to be a discrete I/O point, an input or output. Pin 2 can be a standard I/O pin, or it can be set up as a power pin. The reason, or why or what will happen if pin 2 is set for power. That means as soon as I send down this configuration, pin 2 will be in an on state with 24-volt present always, as long as UA or actuator power is present on the module at the L-coded power cables. Now, for 99% of our customers, you're not going to make any changes here, and you'll leave it all as I/O. The other thing I'm going to do here is I'm going to go to Ethernet IP mapping, and I always forget this, but on this mapping tab, I want to go all the way down to the bottom, and where it says always update variables, I'm going to choose the second option, enable 1, and this will update my I/O. And sometimes I'll forget to do that, and I'm troubleshooting why my process data is not entering the Codesys controller. So at this point, that is the setup. I will save my project, and I will download it to the controller. And it'll finish downloading and be in a stop state down here in the bottom middle. So we are in a stop, so I'll come up here and put it into a run state. And what I want to note here is my Ethernet IP scanner, and my BALF module all show this green circle, meaning that I am connected properly between the BALF module and the Codesys controller. Back over here on the right, Ethernet IP mapping, utilizing the EDS file, it shows our 16 points of input as well as our 16 points of output. We also have diagnostics on the input side for the short circuit, meaning that I have a short between pins 1 and 3. We have overload diagnostics, meaning that I have a overload or a short circuit between the output on pin 2 to 0 or ground, or pin 4 to ground, and there's 16 points there for each individual pin. We also have power status as well, and on the output side we have the output restart bits as well, and I'll explain a little bit more on that here shortly. Just to show that this is working, I'm going to do my split screen here. Here is my module through the web UI. I have the good green lights, US power, which is my sensor power, my UA power or actuator power, those are all solid green. And then my net LED and mod LED are solid green, which I need in an Ethernet IP application. And the lights, the status lights here are showing that I am connected to the left Ethernet port. I am got 100 as my baud rate, because Ethernet IP is either 10 or 100, so this is the 100 LED, and then the blinking here is showing my active communication on that pin. If I did daisy chain to another device on Ethernet IP through the right port, then the two LEDs to the right here would be active in the similar way. So to show that our Codesys setup is working, I'm going to set the first output, so that would be port 1 LED 0 or pin 4. We're going to turn that on as an output and see the reaction of the block. So I'll go to debug, we'll write that value, and we'll see that I've turned on the output in my controller that has set the output on the module. And then on the input side, I have a true state for that input as well. The input side is simply showing whether there is 24 volts presence or not. And then the output is actually telling the module itself to put 24 volts on that corresponding pin. These modules are freely configurable, And really what that breaks down to is you do not have to configure the pin as input versus output. If I want to use the pin as an output, I'll simply put the output address on a coil in my logic, and when that coil is energized in my logic, the corresponding pin will come on with 24 volts on the module. All right, so that is where freely configurable comes in. If I needed to swap out this module, I don't have to do anything special outside of setting the protocol and the correct IP settings. And the logic will dictate which pins are inputs versus outputs. The way the I/O is explained here is pretty good, but I wanted to show you here in ending here. The video is the actual breakout of the I/O points. So I broke this out just like any typical thing. There's 8 bytes of input data, 6 bytes of output data. Byte 0 and 1 are your corresponding inputs, as you see here. So we go pin 4, pin 2 of that port. So bit 0 in byte 0 is port 1, pin 4. Bit 1 is port 1, pin 2, and then so on. Bytes 2 and 3 are the short circuit. It doesn't matter which pin or which bit you use, they both will come on and off at the same time with a corresponding short circuit. Then you have your overload diagnostic per pin, and then you have byte 6 with your diagnostics for your incoming 24 volts on the power connection. So if bit 0 comes on, that's low actuator or output power, meaning it's below 18 volts. Low sensor power is below 18 volts on the US power. And then no actuator power is when we've dropped below a voltage level where we actually turn off or disable any outputs from coming on, because if the voltage level drops to a certain point, we feel it's unsafe for those outputs, and we will turn on this diagnostic bits and no more outputs will energize. Typically, if this bit is on, it's because there's simply no output or actuator power to the module, because a safety circuit somewhere within the power system has dropped that power. On the output side, you've got byte 0 and 1 are your 16 points of outputs, named similarly or laid out similar to the inputs. And then you have 16 points for the overload status, a bit for each pin. What happens in this module if we go into an overload state? That overload state is latched, and you can only unlatch it through a cycle of power or by toggling the corresponding overload reset bit. So if you wanted to reset an overload via logic, you would use these overload reset bits. Finally, within the output buffer, if you are using the BNI00L8, which has the display, byte 5, bit 0 would turn the LEDs on the display red, while bit 1 turns those LEDs green, and bit 2 being turned on would lock the display. You can view and you can navigate the menu, but you cannot make any changes to the settings if the display is locked through the controller. So I hope that aided you or will aid you in the future on setting up a BNI00L7 or a BNI00L8 from Balluff within a Codesys environment using the EtherNet IP protocol. Thank you.